Alright, ladies and gentlemen, the moment you've all been waiting for, it's chemistry. So tonight we're going to talk about some of the most exciting parts of redox reactions, and that is how to balance them. Before we do that, we've got to talk about acidic solutions and redox reactions. So we looked at what happens with strong acids like hydrochloric acid and sulfuric acid, but we said that was except for nitric acid. Well, now here's the nitric acid part. So with nitric acid, we're actually concerned with the nitrate rather than the H+. So in nitric acid, the nitrate, the NO3, can oxidize a metal that the other strong acids cannot. So if HCl can't oxidize a metal, nitric acid more than likely can. So what winds up happening is the NO3 in the solution will take the electrons away from the metal to make the metal into a cation and form nitrous oxide gas. This is a very common reaction. It's very recognizable because the NO forms kind of like a reddish-brown gas. Really gross-looking cloud that's actually pretty bad for you to breathe in. So here's an example of copper metal being oxidized by nitrate. So that means the copper metal is losing 2 electrons to the nitrate, forming the NO and then the Cu. Now here's the problem. If you try and balance this reaction, remember you've got to balance for molecules and for charges. So molecules works out 1 copper, 1 nitrate, NO3, and then NO. So if we try and balance those oxygens, we would put a 3 right there. Well, now we've got 3 nitrogens too, so we've got to put a 3 right there. Well, now we've got 9 oxygens, so we've got to put a 9 right there, a 9 right there. Well, now we've got... Yeah, you see where I'm going with this? It doesn't work, and that's because there's more going on than just the transfer of electrons. So we've got to use a different method for both writing and balancing this reaction. Now at this point, I should point out that it is not the nitrate itself that is oxidizing the copper, it's the nitric acid. And so what I mean by that is if we consider something like copper in a solution of sodium nitrate. So remember sodium nitrate, that's really Na plus, NO3 minus, and so we could think of this as Cu plus NO3 minus. And you might be tricked into thinking, okay, hey, nitrate, I know how that reacts with copper, it produces NO and Cu2 plus, but that's not the case. In this instant, there would be no reaction. That's because it's not just the nitrate, it's the fact that the nitrate is surrounded by H plus ions. And it's what we call a redox in an acidic solution. So that's kind of a hint as to what's coming next. So I'm going to show you how to balance a redox reaction then in an acidic solution. And so that solution, it can be really any acid, like nitric acid that we just talked about, or hydrochloric acid, sulfuric. You'll see a variety of different ones. But you recognize these problems because they'll specifically say, hey, here's a reaction that's taking place. It's taking place in an acidic solution. So that means you'd use this method then to balance it. So if you're taking notes at home, just go ahead and write these down, and then we'll go through each individual step one at a time. First off, though, the most important step is going to be this one right here, which is writing those oxidation and reduction half-reactions. So we actually have to do this whole balancing thing twice. We have to balance both of the half-reactions on their own individually. All right, let's do the reduction half first. So step number 1 is to write the reduction half-reaction. Now hopefully you've got some practice with this and you're familiar with writing half reactions. One of the common mistakes though is breaking apart things that don't need to be broken up. So for example, we have nitrate turning into NO. Now it's really the nitrogen that is doing the reduction because it's going from +5 to +2. And so you might be tempted here then to write, well, nitrogen is turning into nitrogen. But that's not the case. Nitrate has to stay together. You break apart ions, you take out spectators, but you cannot break apart things that are covalently bonded. They're a package deal. Even though it's the nitrogen that is being reduced, we still have to leave them together with its oxygen. So then let's go ahead and write that the proper way. This one's actually pretty easy because the spectators have been taken out already, and so it's just going to be NO3 minus turning into NO. And for the next steps, I'm going to go ahead and shrink this up into the corner and write nice and big so we can all see it. So step number 2 has us balancing the things that are not hydrogen and oxygen. So in this case, that would be nitrogen. We see there's 1 nitrogen and 1 nitrogen, which means that step is already complete for us. We don't need to do anything else there. This step, it turns out, you end up skipping a lot. Do not forget it though. It'll sneak up on you every now and again. You kind of get used to never doing it, so you bruise right past it. Go to step number 3. Be careful though. Always try and just remember to check for the atoms that are not oxygen or hydrogen. Now if you look at this, there's 3 oxygens and 1 oxygen, which brings us to step number 2, how we balance those oxygens. Now I've already showed you if we tried to balance with big numbers, we would wind up going funny because we would put 3 here. That would change our nitrogens and we have to go back and forth and never get anywhere. So instead we have to use waters to balance the oxygens. Alright, so we've got 3 oxygens on the one side and only 1 on the other. So in order to make those oxygens equal, we're going to add 2 waters to this side. As step number 3 says, you use waters to balance the oxygens. Once this is done, you can see that we've got 3 oxygens and 1, 2, and 3 oxygens. What, Mr. Jones? Where did that water come from? There's no water in the original reaction. True, there is no water drawn into the original reaction, but if you look in it, it's aqueous, which means this stuff is dissolved in water. So there's water all around it. We're just saying, hey, we've got to take some of those waters from the solution and start using them in our reaction. So they actually do play a role in the reaction. They're no longer spectators. They are now active participants. But by adding water, we've also added hydrogens to the mix. And that's okay. We just go to step number 4, which says we can balance the hydrogens by using H pluses. So we have 4 hydrogens on this side, which means we need 4 on the other. And so we would add 4 H pluses to this side. What? Come on, Mr. Jones. I'm going to write really big and angry letters in my notebook because where did those H pluses come from? This is in an acidic solution, and H plus is acidic. Remember, this is not nitrate, it's nitric acid. And so these are the H pluses then from the nitric acid that are now playing a role in this reaction. And so to seal the deal, we've got to finish with step 5, which means balancing the charges. So if we look at the overall charges, on this side right here, we have 4 H pluses and 1 negative, which means the overall charge on this side is going to be 3 plus. And then on the product side, we have a neutral compound and a neutral compound, so an overall charge of 0. So to get those to be equal, we can't add any protons, we can't really take anything away. The only thing we can do is add electrons. So if we add 3 electrons to this side, that's going to turn this charge on this guy to 0 as well. So now they match up, and this half reaction is completely balanced. Hey, that was fun, but the good news is that was only half the fun. Now we've got to do the other half of the fun, the oxidation half of the fun. So let me go ahead and shrink this on down, and we will take a look at the guy that's being oxidized, and that is copper. So in this case, it's just copper solid turning into Cu2+. And hey, this will be nice and easy. Step number 1, it's done there, wrote our half reaction. Step number 2, already balanced. Step number 3, ain't no oxygens, ain't got to add water. Step number 4, ain't be no hydrogens either. Don't got to balance for those. So step number 5, let's throw down some charges. On our reactant side, we have a neutral charge. On our product side, we have 2 plus. So that means we're going to have to add 2 electrons to this side to make it so that both sides are at 0. Both sides have the same charge. So if you're following around from the notes on the couple slides back, you would have noticed that we were skipping steps 6 and 7. Now's where we get to 6 and 7. After we've written and balanced those half reactions, we combine them together. So step number 6 has us cross-multiplying in order to get an equal number of electrons. So here we can take a look at our 2 half reactions as written out before. Just type nice and neat. We can see right here where nitrate is gaining 3 electrons and copper is losing 2 electrons. That doesn't match up because this guy needs 3 and that guy needs to lose 2. So in order to get these to balance out, we would have to multiply this top one by 2 and this bottom one by 3. And so then being sure that you multiply everything inside there by that particular number. And what that's going to do is give us 6 electrons on either side. So we can show 6 electrons lost, 6 electrons gained. Alright, now we're going to sum the 2 reactions together, canceling out things that appear on both sides. And in this case, we do have 6 electrons on the reactant side and 6 electrons on the product side, so those will cancel each other out. And, usually we're going to have waters and hydrogens on opposite sides too. In this case we didn't, because we didn't need to use them to balance the copper. So those will not cancel out. When we sum these two reactions together, we're going to get our final balanced redox reaction. So that means there's 2 nitrates, 2 NO3 minus, plus 8 H pluses. So there's our nitric acid stuff going on. And it's reacting with 3 coppers and turning into 3 copper 2 plus the nitrous oxide plus 4 waters. Now this is going to look a whole lot different than an original reaction that we talked about at the very beginning, where it was just copper and nitrate making Cu2 plus and NO. What's happened is we're pulling in some of those guys that are surrounding us, so the H pluses from the acid, the waters that are in solution, and we're turning them into active players in this reaction. So as a result, we can see how this reaction actually takes place, and now it is completely balanced and it will work.